Hi students, welcome to Diamond Group of Institutions, NEET and K-CET online classes. Today we are going to discuss about the magnetism and matter. So before going to start this unit, once practice the formulas and read the theory also. We may expect a theory question from this topic. Okay, now see the first question. A short bar magnet of magnetic moment given 0.4 joule per Tesla is placed in uniform magnetic field of 0.16 Tesla. Magnetic field also given. The magnet is in stable equilibrium. The given stable equilibrium when the potential energy is. So we have to find the potential energy. So already we know the potential energy formula. U equal to minus m dot b, dot product here. So m is the magnetic moment and b is the magnetic field. Okay, so now m dot b expanded, minus mb cos theta. Okay, they given here the magnet is in stable equilibrium. So when the magnet is in stable equilibrium means if the potential energy is minimum, that means minimum, it means here that is equal to minus mb. Okay, then that means the magnet is in the stable equilibrium. If potential energy is maximum mb, then this is in the unstable equilibrium. That means if theta equal to the 0 degree, then this is in the stable. Theta equal to 180 degrees, then it is in the unstable. Okay, remember that one. Okay, now this they mention already the magnet is in the stable equilibrium. If it is in the stable equilibrium, U minimum equal to the minus mb. So U equal to the minus mb. M value they given, that is 0.4 joule per Tesla magnetic moment, and B is the magnetic field. Magnetic field also they given 0.16 Tesla. So now substitute these values in the formula. Minus 0.4 into 0.16, then we will get the minus 0.064 joule. So the option B is the right answer. Okay, now come to see the next question. Second question, the work done in turning a magnet of magnetic moment m. So magnetic moment they given m by an angle of 90 degrees. They are turning the magnet by 90 degrees from the meridian. Okay, is n times the corresponding work done to turn it through an angle of 60 degrees. Through an angle of 60 degrees. The value of n is. That means here we have to do the two cases. First, the magnet is rotated from meridian to the 90 degrees. Okay, and in the second case, meridian to the 60 degrees. In both cases, we have to find the work done. Okay, na? Suppose here we have the meridian. Now magnet is along this one. Now shifting this one to the up to here. So now become the 90 degrees angle. Then what is the work done here? We have to find. Now here the magnet is along the meridian. Now it shifted to the 60 degrees. Then what is the work done? We have to find. That means here along the meridian means theta 1 equal to the 0 degrees. When it rotated to the 90 degrees means theta 2 equal to 90 degrees. And here second case theta 1 equal to 0 degree only along the meridian. Next shifted to the 60 degrees means rotated to 60, theta 2 equal to the 60 degrees. We have the two cases here. Already we know the formula of the work done. Work done ka formula is m into b into cos theta 1 minus cos theta 2. Okay, work done formula is mb into cos theta 1 minus cos theta 2. Theta 1 is the initial angle, theta 2 is the final angle. Okay, so here first case mein theta 1 is a 0 and it rotated with angle 90 degrees. So theta 1 is the 0 and theta 2 is the 90 degrees. So here cos 0 value 1, cos 90 value is the 0, 1 minus 0, 1. So then we will get the work done in the first case equal to the mb. Okay, and the next in the second case theta 1 is a 0 degree and theta 2 equal to the 60 degrees. Now substitute in this formula. So w2 equal to m into b cos theta 1. Theta 1 value is a 0, theta 2 value is the 60 degrees. So now w2 equal to the mb into cos 0 value is 1, cos 60 value is 1 by 2. So 1 minus 1 by 2 value is the 1 by 2. So we will get w2 equal to mb by 2. So now from this we can get 2 send this side, so MB equal to the 2W2 we will get, MB equal to the 2W2. Now equate these two equations, so W1 equal to MB, MB equal to 2W2, so then W1 equal to how much? 2W2. That means work done by the angle 90 degree from the meridian is n times the work corresponding work done to turn it through an angle of 60 degrees. That means the work done by the first case में W1 and second case में work done equal to the MB equal to 2W2, W2 equal to MB by 2 we got. So equate we will get the first work done is equal to the n times the second case में work done. N is equal to how much? 2. Okay, 2 times. Now 2 is the right answer, C option. Okay, next question is the third question. A bar magnet of length L and a magnetic dipole moment M bent in the form of an arc as shown in the figure. The new magnetic dipole moment will be. Okay, so here you have to remember the direct formula. Actually, if we go through the derivation, it will take nearly 5 minutes time. If you use the formula, within 15 seconds we will get this one. So they are taking any dipole moment M and bending by making some angle here. Okay, they given 60 degrees also. Then what is the new magnetic dipole moment? To find that one, new magnetic dipole moment equal to the initially magnetic dipole moment into sine theta by 2 theta by 2. If you use this formula, you will get within 15 seconds answer. So now initially the magnetic dipole moment they given m into sine. How much angle it is making? After bending, it is making the angle 60 degrees. The angle between the two ends is 60 degrees. So sine theta is nothing but the 60 by 2, theta by 2 means 60 by 2. So sine 60 by 2 is nothing but the 30 and 60 by 2 is nothing but the 30. Write down in the terms of the radians, pi by 6 radians. So now m into sine 30 value is 1 by 2, either pi by 6 is there, reverse it 6 by pi. Simplify, we will get the new magnetic moment equal to the 3 by pi into m or 3m by pi. Okay, so D option is the right answer. Okay, next question, fourth question. At a given place on Earth's surface, the horizontal component of Earth magnetic field is, horizontal component of the Earth magnetic field they given 2 into 10 power minus 5 Tesla, and the resultant magnetic field is 4 into 10 power minus 5 Tesla. The angle of dip at this place is, angle of dip we have to find. Angle of dip is nothing but the angle of inclination. Okay, so angle of inclination we have to find here. So now suppose this is, we consider it is a magnetic meridian. So in this magnetic meridian, so this is the resultant magnetic field. So this resultant magnetic field divided into the two components, horizontal component and vertical component. So horizontal component equal to B cos del and vertical component equal to B sin del. So here this horizontal component is along the surface of the earth. So now the angle made by the resultant magnetic field with the earth surface is called as the angle of dip or angle of inclination. Otherwise, the angle made by the resultant magnetic field with the horizontal component of the magnetic field is nothing but the angle of dip or angle of declination. Okay, so from this we can write it as, here we know the BH equal to B cos del and BB equal to the B sin del. So they are asking the they given the horizontal component of the magnetic field and the resultant magnetic field, they are asking the angle of dip. So use this formula we will get. And the next one more thing is that, suppose this plane is there, this is meridian is nothing but the geometrical meridian and this is nothing but the magnetic meridian, then angle between the geographical meridian and magnetic meridian is nothing but the angle of declination. This is the angle of declination and this is the angle of inclination. For this magnetic meridian, so this is the resultant magnetic field, this is the horizontal component, this is the vertical component, and this is nothing but the angle of dip or angle of declination. So angle between the geometrical meridian and magnetic meridian is nothing but the angle of declination. The angle between the resultant magnetic field and with the horizontal component of that magnetic field is nothing but the angle of dip. This is also nothing but the angle between the resultant magnetic field and with the surface of the earth. Okay, remember this definitions. Okay, now they given the horizontal component of the magnetic field and total magnetic field. They are asking the angle of dip. We will use this formula. So BH equal to B cos del. So BH value is, horizontal component value is 4 into 10 power minus 5. Sorry, total magnetic field value is 4 into 10 power minus 5 and horizontal component value is 2 into 10 power minus 5 Tesla. So now cos del equal to BH by B, we will get BH value and B value substitute, we will get the 1 by 2. So in cos we will get the 1 by 2 for cos 60 degrees. So from this del equal to the 60 degrees, which angle of dip or angle of inclination is equal to the 60 degrees. In this way we have to solve the problem. Next, see the next question. The coil in a tangent galvanometer is 60 centimeter in radius. Radius they given 16 centimeter. How many turns of the wire should be wound on it? So if a current of 20 milliamperes, 20 milliampere current is to produce a deflection of 45 angles. Deflection they given 45 degrees. Take horizontal component of earth field. Horizontal component also they given. Already in the theory you know about the tangent galvanometer. That means we are taking one magnetic compass and keeping in the direction of the horizontal component, horizontal component direction. Then here suppose we are applying the external magnetic field to this magnetic compass, then this magnetic compass will get the deflection. Okay, so here due to this horizontal component it is exerting the force and this external magnetic field also exerting the force. Okay, so this is exerting the force and this one is exerting the force. Due to that one, at some point it will come to the, it will make some angle and it will stop there. Okay, so that means due to this one producing the torque, this horizontal component is producing the torque and this external magnetic field also producing the torque. So whenever this two torque, the torque produced by the horizontal component of the magnetic field and this external magnetic field are equal, then this will be stay stable. Okay, it is in the equilibrium. Okay, then here suppose if it is making some angle theta with the horizontal component of earth magnet, so then the torque produced by this one is nothing but the, already we know the torque formula, tau equal to the m cross b or mb sin theta. mb sin theta, already you know this one. Suppose here this magnetic compass is tilted by some angle theta with the horizontal component of the earth magnetic field, some angle theta I am assuming. So then torque equal to the torque produced by the horizontal component equal to the mb sin theta and torque produced by this external magnetic field. So if this magnetic compass is making theta angle with the horizontal component of the earth magnet, then what is the angle made by this one? This total angle is 90. This angle is nothing but the 90 minus theta we will get. So torque is mb sin theta. So now angle made by this magnetic compass with the external magnetic field is 90 minus theta. So mb sin 90 minus theta. This torque is due to the external magnetic field. This torque is due to the horizontal component of the earth magnet. So that's why I kept here magnetic field external, here the horizontal component of the earth magnet here. So either this magnetic compass making with the external magnetic angle is 90 minus theta and here this horizontal component of earth magnet making the theta angle. So then I substituted here theta plus my 90 minus theta, here theta plus my theta as precisely. Okay, now mb external into sin 90 minus theta is nothing but cos theta. Here same thing I will get. Okay, so my m will be cancel, magnetic moment. Okay, so b external equal to cos theta sin this side, sin theta by cos theta equal to tan theta we will get. That means the external magnetic field equal to the horizontal component of the earth magnet into tan theta. Theta is nothing but the how much angle deflected with respect to the horizontal component of the earth magnetic field. Okay, now suppose here they given the one circular coil, that means current is flowing through the coil. Okay, so that coil, if a coil produces the magnetic field, how much magnetic field it is producing? Already we know the formula. So the magnetic field produced by the coil is nothing but mu naught I by 2r, mu naught I by 2r. Suppose if n number of turns are there, we have to multiply with the n. So n into mu naught I by 2r equal to bh tan theta. Now we have to find the n. So remaining terms send this side. So n equal to 2r will go to the numerator and mu naught I will come to the denominator. So bh tan theta into 2r by mu naught I. So now n equal to the horizontal component of the earth magnetic field they given, horizontal component of earth magnetic field 0.36 into 10 power minus 4 Tesla. So 0.36 into 10 power minus 4 what tan theta, angle deflection equal to the given 45 degrees, so tan 45 equal to the 1, so 1 I written here. And next 2 is 2 radius they given 16 centimeters, convert into the meters, 16 into 10 power minus 2 meters. And the next in the denominator we have mu naught value is 4 pi into 10 power minus 7, already we know. I value, current value also they given 20 milliamperes, convert into the ampere, 20 into milli means 10 power minus 3. Simplify all this, we will get the answer. Number of turns equal to the 458. So option D is the right answer. Solve in this way. So this is the for your understanding purpose I explain this one. Just simply you have to use the final this result only. B external equal to BH into tan theta. No need to do these steps. Remember this formula and proceed the next. Okay, come to see the next question. The given figure shows the variation of intensity of magnetization versus the applied magnetic field intensity. That means here they given the figure here. On the figure they are taking the intensity of the external magnetic field and the intensity, that means intensity of the magnetization. Okay, due to this external magnetic field, how much magnetic field is developing in the materials. We have the 3 type of materials. Okay, that also they given for 3 magnetic materials A, B, C. Name the diamagnetic, ferromagnetic and paramagnetic materials. These are the given. Okay, so for here you have to remember one thing here. For this if we apply the external, if we keep the diamagnetic material or paramagnetic material or ferromagnetic material in the external field, how this intensity of magnetization developed in that materials. Okay, from theory you will get that one. So suppose if you take the diamagnetic materials, so here the induced magnetic field direction is opposite to the external magnetic field and that is the weak. Okay, that means the intensity of the magnetization is the weak and opposite to the external magnetic field. So that means the intensity of the magnetization weak means negative and opposite to the external magnetic field. So C is nothing but the diamagnetic material. Okay, if we come to the paramagnetic material, for paramagnetic material, if we keep in the external magnetic field, so the induced magnetic field in the direction of the external magnetic field only, but the intensity of the magnetization is the low. Okay, low only but along the external magnetic field only. That's why the value is low, positive only, but it is in the direction of the external magnetic, but it is the low, positive and low. Okay, this is indicating that paramagnetic material. Okay, now come to see the ferromagnetic material. So ferromagnetic material keep in the external magnetic field, so the induced magnetic field is the large compared with the paramagnetic material. In paramagnetic material also magnetic field in the induced magnetic field direction is same in the external magnetic field. In ferromagnetic material also the induced magnetic field direction is along this external magnetic field. In both cases along the external magnetic field only, but induced magnetic field strength in ferromagnetic material is very strong compared with the paramagnetic material. That's why the slope of the ferromagnetic material graph is more. So A is indicating the ferromagnetic material. So A is indicating the ferromagnetic material and B is indicating the paramagnetic material and C is indicating the diamagnetic material. So see now A is F, B is P, C is D. So option B is the right answer. Next question, 7th question. A solenoid has a core of material with relative permeability of 500. Relative permeability they given 500. The windings of the solenoid are insulated from the core and carry a current of 2 amperes. 2 amperes current carrying. If the number of turns is 1000 per meter, number of turns small n. Okay, then magnetization is, what is the magnetization? We have to find. This problem is totally based on the formulas only. So magnetization means symbol is IRM. Okay, that we have to find. So next here, the magnetic field is depending on the current flowing through that wire and number of turns. So the intensity of the magnetic field H equal to the N into I. N is nothing but the number of turns per unit length and I is the current. So number of turns per unit length they given 1000 per meter. So 1000 turns they given. I current is flowing through that one is the 2 amperes. So 2000 ampere per meter is the intensity of the magnetic field, external magnetic field. Due to this field, how much magnetization is developing in the core, that we have to find. So the relationship between the intensity of the magnetization and intensity of magnetic field का formula m or I equal to mu r minus 1 into h. Mu r is the relative permeability, h is the intensity of magnetic field, m is the intensity of magnetization. Okay, so now mu r value is given, permeability of 500 minus 1 into h value we found already 2000. So substitute here, 500 minus 1 is the 499 into 2000, then multiply, simplify, you will get the answer 9.98 into 10 power 5 ampere per meter. 9.98 10 power 5 ampere per meter. C is the right answer. So totally based on the formulas. Remember formulas. Next, see the next question. A bar magnet is oscillating in the earth magnetic field. Bar magnet is oscillating in the earth magnetic field with a time period t. What happens to its period and motion if its mass is quadrupled? So motion not changes. Previously what is the motion? Is there same motion? Previously simple harmonic motion is there, now simple harmonic motion only. Now time period. So if a bar magnet is oscillating in the earth magnetic field, then the formula for this one is time period equal to t equal to the 2 pi into root I by mb. I is nothing but the moment of inertia of magnet, bar magnet. M is the magnetic moment behind the external magnetic field. Okay, that means earth magnetic field. So now here this we are not changing, only moment of inertia formula we know, m into k square. Okay, remember the formulas. From here the relationship they are saying, they are doing means here mass is quadrupled, so it become the 4 times. So now then just we have to find out the relationship between the time period and mass. So time period is directly proportional to the square root of m. So t2 by t1 equal to square root of m2 by m1. Initially m1 equal to m, then m2 equal to quadruple to 4 times. So now 4 into m will be cancelled, square root of 4 is 2. Now t2 equal to the 2t1. t1 value already given. Initially the time period is t. Initially time period is the t. So now finally the time period becoming the 2t. So 2t is the right answer. Motion is not changing, but time period is changing to the 2t, double to the initial time period. So B is the right option. Now come to see the next question. The length of magnet is large compared to its width and breadth. The time period of its oscillation in vibration magnetometer is 2 seconds. Time period they given 2 seconds. The magnet is cut along its length into 3 equal parts. Here magnet is cut into the 3 equal parts. These parts then placed on the each other with their like poles together, the time period of the combination will be. So the time period of the combination will be. Okay, if they ask this type of question, use the shortcut. Okay. So now for the time period for the vibration magnetometer, your previous question we written that formula, t equal to 2 pi into root I by mb. Okay, if the magnet is cut into 3 equal parts, how this moment of inertia changes? So the moment of inertia of each part equal to the I by n cube. I is the initial moment of inertia and n is nothing but the how many number of turns we are, how many number of parts we are making. Okay, so then each part ka moment of inertia equal to I by n cube. How many parts they are making? 3. So 3 cube means 27. That means the moment of inertia of the each part equal to the I by 27. How many parts they are making? 3 parts. 3 parts ka moment of inertia 3 into I by 27, then it will become I by 9. Okay, remember that point also. Next, magnetic moment. Okay, if the magnet is cut into 3 equal parts, how the magnetic moment changes? So magnetic moment of each part equal to the m by n. So m is the initial magnetic moment and n is the number of parts. So here this magnet is divided into the 3 parts. So then the each magnetic moment is m by 3. Okay, so remember that means here they given the 3 magnets ka magnetic moment also, we can 3 parts ka magnetic moment also find it. And next one is the time period. If these 3 parts, the magnet is cut into the 3 equal parts, then what is the new time period? So remember the new time period equal to the t by n. So initial time period by the n is nothing but the number of parts. So T by N is nothing but initially time period is the 2 seconds they given, and how many parts they are making? 3 parts. So now time period equal to 2 by 3 seconds. B is the right option. Okay, like this you have to solve the problems.
Next question, 10th question. Two bar magnets. So they given the two bar magnets having the same geometric magnetic moments. Magnetic moments given M and 2M are firstly placed in such a way that the similar poles are on the same side. Similar poles are in the same side. I drawn here. This is the first one magnet and this one is the second magnet. These are arranged similar force in the same side. So north on the same side, south the same side. In the first case, time period of oscillation is T1. In this case, the time period equal to the T1. Now the polarity of one of the magnet is reversed. Then the time period of oscillation is, so now top one is the north south only there. Now this will become the north side here, south side here. So polarity is changed. In the first case, both same sides. That means here similar poles are same side. North to north, south to south. Here unlike poles are same side. North to south, south to north. So in this case, time period is a T1. In this case, time period is a T2. And they are asking what is the relationship between the time period T1 and T2. So we know already the time period of revolution formula T equal to 2 pi into root I by mv. This is the formula. So that means if both the poles are same, similar poles are same side and unlike poles are same side, how the magnetic momentum and moment of inertia changes. If we change the polarities, the magnetic moment of inertia not changes. Okay, na? If we change the polarities, moment of inertia not changes. That means in the first case moment of inertia, in the second case moment of inertia, both the cases means same. That means in the first case moment of inertia is Is means the same side. Okay, same side I am keeping the polarity. So Is equal to I1 plus I2. In the second case also reverse, polarity is reverse equal to I1 plus I2. So if you change the polarities, moment of inertia not changes. Now come to see the magnetic moment. So if the similar poles are same side, then magnetic moment are equal to sum of that magnetic moments. So magnetic moment is same side polarity is there, then M1 plus M2. Okay, M1 plus M2. Sum of the magnetic moments. And unlike poles are there in same side, unlike polarities, north and south there, then resultant magnetic field. That means here we are reversing the direction. That's why I keep the reverse. M1 minus M2. Polarity, same polarity, same side. So magnetic moment is sum of the two bar magnets. And unlike poles, same side, then magnetic moment of that system, the two magnets is nothing but the difference of magnetic moments. So moment of inertia is not changing, magnetic moments is changing. Okay, then time period for apply to T equal to 2 by root I by mv. So now from this case, we can write down the relationship between the moment of inertia and magnetic moment. That T is directly proportional to the I by mv. So now, if same side are there poles and if reverse polarities are there, then so same side by inertia of same side by inertia of magnetic moment of same side, and square root of reverse polarities are reversed, then moment of inertia by magnetic moment. Okay, now here simplify this one. Is by ms totally square root I am writing mr by ir. So both the cases में magnetic moment of inertia is same. Both the cases moment of inertia is same. Cancel out. Then we will get the mr by ms. Mr makes if polarities are reversed, magnetic moment. Ms makes if polarities are same side, then magnetic moment. So reversible m1 minus m2. Same side m1 plus m2. So m1 minus m2 by m1 plus m2. They given the magnetic moments. One magnet का m, other magnet का 2m. m1 minus m2 minus 2m minus m, and sum of that means m plus 2m, 3m. So mm cancel 1 by root 3 we will get. So from this T1 equal to T2 by root 3. T1 is nothing but whenever the same side polarities are same side, then time period is the T1. If the polarities are reversed, the time period is the T2. So T1 by T2 equal to 1 by root 3. T1 equal to T2 by root 3. That means if we divide the T2, we will get the T1. So T2 is more than the T1. T2 is greater than the T1. This one we can write as T1 is less than the T2 or T2 is greater than the T1. The option A is the right answer. Now come to see the next question. The electron in the hydrogen atom is moving with the speed. Speed they given 2.3 to 10 power 6 meter per second in an orbit of radius they given 0.53 angstrom. The magnetic moment of the revolving electron is. Okay, the magnetic moment of formula due to the movement of the electron, current is flowing through that one. So due to that, magnetic moment of formula is I into A. Already magnetic moment of formula I into A. And it is revolving in the circular path. The area equal to the pi r square. So now here we have to find the current, and we have to find the we need the radius. Radius value already given 0.53 angstroms, but we have to find the current. So how to find the current? Current the formula we know I equal to the Q by T. Okay, Q means charge, electrical charge, 1.6 into 10 to the minus 19 coulombs. And time we have to find. How to find the time means it is revolving in the circular path. So the time period is equal to the circumference of the circular path by motion of the or velocity of the or speed of the electron. Okay, so 2 by r by v. So 2 pi into radius they given, velocity also, speed also they given 2.3 to 10 power 6 meter per second. After simplification we are getting the time period 1.448 into 10 power minus 16 seconds. Okay, time period we got, charge already we know, electron ka charge, find the current. So current value I am finding. So current value we got 1.1 to 10 power minus 3 ampere. That means Q charge the 1.6 into 10 power minus 19. Time period already we found 1.44 into 10 power minus 16. Simplify, we will get the 1.1 into 10 power minus 3. So now I value we got already radius they given. So now substitute in this formula. Magnetic moment is equal to the I value is 1.11 to 10 power minus 3. Pi value is 3.14. R value they given 0.53 angstroms. So 0.53 into angstrom is 10 power minus 10 meters. So all square. Simplify, we will get the magnetic moment equal to the 9.8 into 10 power minus 24 ampere meter square. This is the magnetic moment. So option D is the right answer. And from based on this one more important formula also there. So if electron is revolving in the first orbit, the magnetic moment this is also called as the Bohr magnetron. Okay. So mu equal to actual formula is NEH by 4 pi m. If it is revolving in the first orbit, then magnetic moment is nothing but the EH by 4 pi m. Then this is also called as the Bohr magnetron. Okay, now if the key question can be asked based on this one also, so many times asked, that's why I am saying Bohr magnetron or magnetic moment of electron in first orbit EH by 4 pi m. By using this also we can solve nearest value we will get. Okay, thank you. Practice the problem seriously.